All right, hello, welcome, and thank you for attending today's EERI webinar hosted by our Younger Members Committee on real-time hybrid simulation for earthquake-induced motions and cascading earthquake and tsunami events. I just want to take my name is Elizabeth Angel. I'm EERI's Communications and Program Manager. And if you're not familiar with us, I wanted to take a brief moment to introduce us. The Earthquake Engineering Research Institute is the leading nonprofit membership organization bringing together people from a wide range of disciplines who work to advance earthquake resilience and better understand earthquake risk, both in the United States and around the globe. And we'd love to have you join us as a member. If you're not one, you can find out how to do that at that link there at the bottom of the page. I also want to let you know, especially those of you who are based in California, about our upcoming annual meeting in San Francisco next month, which will include a one-day technical program focused on earthquake reconnaissance, or the past, present, and future of post-earthquake reconnaissance efforts. It will include a special session as well on the recent earthquake sequence in Turkey and Syria. There will be an early career workshop. There'll be a reconnaissance workshop and exercise, the undergraduate seismic design competition, which is always a great time. So you can find out more about that and register at this website. And there's, I think, 1 week left to register at an advanced rate. So we hope to see you there. And on that note, I'm going to turn it over to Kostas Kalfas, who's our moderator today on behalf of the YMC.
Okay. Hello, everybody. Thank you, Elizabeth. So hello from the Young Members Committee of EERI. We are a group of young engineers and early career professionals and academics. And I would like to invite any young engineer who is interested in earthquake engineering, seismology, and resiliency against any natural hazard, I could say, to join us because this is a great opportunity for us to socialize and meet with other engineers, make a good network. You can get involved in plenty subcommittees of the EERI. And having said this, I would like to introduce our first speaker, who is Liang Cao. Liang received his PhD in civil engineering from Iowa State University with a minor in electrical engineering. He received his MSc from the State University of New York at Buffalo. His expertise is on increasing the resiliency of structures against man-made and natural events through high-performance control systems. And he will be our first speaker on this interesting topic on hybrid simulation testing. So, Liang.
Thank you, Kostas. So I'm gonna share my screen.
Just while Kostas is getting his while you're getting your presentation up, just a note on the Q&A format for the audience. So we're going to have both presenters speak, and then we'll have a question and answer session. But you can use the Q&A tab at the bottom of your Zoom screen to write your questions during the presentation. So go ahead and put them in as you think of them, and then we'll get to them at the end.
Okay, so good afternoon, everyone. So my name is Liang Cao. I'm a research scientist at Lehigh University. It's a pleasure for me and to present at the EERI seminars. So I would like to introduce a brief work about NHERI. So the NHERI stands for Natural Hazard Engineering Research Infrastructures. Is a nationwide network of facilities held for the natural hazard engineering research communities, and it's funded by the NSF, and almost like 12 universities are in the network. So both Stanford and Lehigh are in the NHERI network. So you're gonna hear something in my presentation. I gotta talk about NHERI Lehigh. Basically, I'm emphasize the NHERI Lehigh facility. So first, I would like to acknowledge the collaborators in the research. They are Dr. James Rickles. He's the professor at civil engineering departments in Lehigh Universities. Dr. Shafwan, he's the postdoc researchers at Lehigh. And Thomas Marullo, he's also a research scientist at Lehigh Universities. And the people outside Lehigh are Dr. Austin Downey. He's assistant professor at the University of South Carolina. And Dr. Simon Leflam, he's a professor at Iowa State University. So here is my today's outline. So first, I'm gonna to introduce the real-time hybrid simulation backgrounds, and also I'm gonna show you a new systems we proposed called high-performance control systems, and then I gotta demonstrate some real-time hybrid simulation applications using these high-performance control systems, and conclude my presentations. So here's the overall concept of the real-time hybrid simulations. So what is the real-time hybrid simulations? Maybe this is the first time you heard this word. So it's combinations of both numerical simulation and experimental testings. So typically, it consists of two substructures we call analytical substructures and experimental substructures. So it's different than the numerical simulations. We are not only numerically modeling the structures, but there's part of the structures where if their dynamics is too complicated or it's hard to model, we build it in the experimental lab. So basically, so here's the flow chart of these hybrid simulations under multi-hazards. So it consists of simulation coordinators to integrate equations of motions. So this equation of motion is pretty simple. It's follow the Newton laws. And once the simulation coordinators receive the real-time excitation inputs, such as earthquake or wind, it automatically calculates the command displacement for both analytical substructures and experimental substructures. And after it receives the restoring force back from these two substructures, it can compute the real-time structural response. So the hybrid simulations concept is simple, right? And why we have to do the real-time hybrid simulations. So the benefit of hybrid simulations is it enables cost-effective large-scale dynamic testings. By comparing with large-scale testings, because you numerically model a portion of your structures in the computers, so it providing a cost-effective method. And also because you numerically model these structures in the analytical substructures, you can using different type of analytical substructures to testing the same experimental specimens. And also I want to highlight why we have to do it in real time, because real-time hybrid simulations accounts for rate dependence of physical specimens. For example, viscous damper-based isolators, as long as their dynamic behavior is related with the velocities, it's not possible to do it with conventional slow hybrid simulations. You have to do it in real time. So the concept of the hybrid simulation is pretty simple, right? But still, for the implementations, it have different type of issues and challenges in both simulation coordinators and analytical substructures and experimental substructures. I'm going to introduce the challenges for both part and also going to propose our solutions at NHERI-EF facilities. First, for the simulation coordinators. So first, we need to have accurate numerical integration algorithms, and we prefer to using explicit integration schemes. What does explicit scheme means the current step has to be calculated by the previous steps. There's no iteration involved. Because if you only do the numerical simulations, it doesn't matter. But if you want to do it in real time, as long as there's iterations, it may not converge at each time step. So if you have iterations in there, so it's always been challenged to do in the real time. And also you have this integration scheme has to be unconditional stable, because you're also adding a physical element in there, right? So if your simulations become unstable, it can destroy your physical experimental specimens. Also, we prefer to adding some numerical damping inside the integration scheme, because you always get noise from the your experimental lab, right? And those noise can be also give you unstable behaviors during the simulation. So that's why we prefer a new solutions called experimental model-based integration or algorithms. So this method we call the explicit modified KR alpha methods, MKR methods. So basically it's explicit integrations, and you can see its formulas. So all this velocity and displacement update is based on the previous steps. So it's basically explicit. And also we are introduced something called low infinity number, which is controllable numerical damping, which is by only changing the row infinity number, you are able to controlling the numerical damping from 0%. You see in this graph, on the right graph, when the row infinity number equal to 1, you have a 0 numerical dampings. And when your row infinity number equal to 0, you almost have 100% numerical damping in very high frequencies. So this is the benefit for this logarithm because it's only one parameters. And by controlling this one, you're easily to adjust numerical dampings. Sometimes for earthquake simulation, you may need a slightly higher numerical dampings, but if under winds, you may just need a very low numerical dampings. And next, for the analytical substructures, we want to have a fast and accurate state determination procedures because you need this you need to determine your restraining force in the real time, right? So that's why we propose to using explicit force-based fiber elements. So what's the difference between the force-based fiber element and displacement-based fiber elements? They both have a benefit. For displacement-based fiber elements, because the curvature varies linearly, so the state determination is straightforward, right? And however, it's a challenge to doing in the real-time hybrid simulation because it requires a big number of elements per each structure numbers. It can significantly increase your number of degree of freedoms, especially when you try to modeling the nonlinear behaviors. So those higher number of degree of freedoms can be a cue for the real-time hybrid simulations. That's why we prefer to do the force-based fiber element because the model material nonlinearities can be modeled using just one single element per structure members. It can significantly reduce the number of degrees freedoms. However, the force-based fiber element still have its own obstacles because it requires iterations at element levels. It can jeopardize explicit integrations, right? So here, this is our solutions. We proposed these explicit force-based fiber elements. So it have all the beneficials from the force-based fiber elements. So you can reduce degree of freedoms by only using one single element per each structure member. And the benefit for this element is it has a fixed number of iterations during the state determination schemes, and it carry on the unbalancing force for the next steps. So I'm not going to describe these elements in details, but if people are interested, you can always find these force-based fiber elements in this journal, in these papers published on 2018 on Journal of Structural Engineering. So for the experimental substructures, the challenge will be you always need a large capacity hydraulic system and the actuators because you try to do full scales, right? And also, so in Lehigh, we have this different type of large hydraulic power supply system and also dynamic actuators, so it won't be issues. But I think the most difficult challenges is the delay because we're dealing with hydraulic actuators, hydraulic systems. You always have a delay in there. So you need compensators to compensate this delay because those delay can add in a negative damping in the simulations, which is also can bring your simulation become unstable. So our solutions to these challenges is we proposed a compensator we call adaptive time series compensators. It's really simple compensators. It's just the principle of this compensator is to minimize the error between the target specimens and the measured displacements using least square method. So the key word is adaptive because your different dynamic behavior, different displacement vibration response. You will once you're using hydraulic system, you may have different time delay. So that's why you always want to using adaptive compensator to adapt the time delay. This compensator is also published in this paper on 2013. So after I introduce the hybrid simulation background, so I'm gonna switch the topic a little bit on high performance control systems. Let me introduce what is high performance control systems by talking about the typical natural hazard mitigation solutions on structures. In general, there's three ways to mitigate natural hazards. Right. First, it will be structural system modifications. You can always modify your structure members, adding bracings in the structures. to dealing with natural hazards, right? But the biggest obstacle is uneconomical. And also it's difficult for implementations on existing buildings. You can't just replace the column for the existing buildings easily. So the second way is you're using passive damping systems such as viscous damper-based isolators. So they are good and effective, but sometimes they typically designing for single type of hazards because their properties, because all these damping systems, their dynamic behaviors is not changeable after they've been manufactured, right? So basically means you give certain input, you got a certain output. So it have a limited bandwidth for multi-hazards. And then what we propose and preferred will be high-performance control systems. So those high-performance control systems, including active, semi-active, and hybrid damping systems, basically it's different than the passive damping system because its dynamics is adjustable. So it's applicable to broader range of excitations, ideal for multi-hazards. And also it have a lower energy input for large energy dissipations. I'm going to talk about this in the next couple of slides by what I mean about lower energy input. So I'm going to introduce one of the high-performance control system we proposed. A couple of years ago, we call banded rotary friction dampers. Basically, is utilizing existing membrane technologies. It consists of three major components: a braking drum and a frictional band wrapped around on the braking drum, and then two connections on bottom, and then the bracing connections to connect to the structures. Basically, the damper force is coming from the friction between the frictional band and the drum. And then we're using a screw type of actuator mechanism to hold the braking band on the braking drum. By adjust the tension force on the braking band, you can adjust the normal force on the braking drum, which is increase the normal pressure on the friction materials, and then you can achieve a controllable damping force. So we published these dampers on 2016, but at that time, we didn't think about that much details on the actuator mechanisms. So we just using a screw to adjust the tension force. Basically, at that time, we are only able to use it as a passive damper, even it have these semi-active mechanisms. So recently, we rebuilt these structures we call second generations in NHERI-EF facilities, where we are using two electrical actuators to controlling the damper, the tension force on the frictional band. And we also installed two load cells between the actuators and the friction band to give actual measurements of the tension force. Then you are able to controlling this tension force in the real time and to achieve its semi-active potentials. So here is the characterization test results. Basically, the left one is force displacement and the right one is force velocities. So we're using harmonic displacement input under different tension force, and indicate is energy dissipation loop. And the tension force we use is 50 to 70 pounds tension force. And you can see by utilizing 70 pounds tension force, we're able to achieve almost 5,000 pounds damping force. We have force application factors of 71. So this is what I mean by using a lower energy input, only 70 pound tension force to achieve higher damping force. So for the next, I'm gonna show you some real-time hypersimulation applications utilizing this banded rotary friction device we call BRFDs. The first I would like to show you is application on an earthquake on two-story reinforced concrete buildings. So in here, we numerically model a two-story reinforced concrete moment-resisting frame. Here are some information on these analytical substructures. We have 32 nodes, 30 elements, and 71 degree freedoms in totals. And we also model the P delta effect by using the linear columns. And then the time step for hybrid simulation is 2/1024. And we assume we install these dampers in the bottom floor. So because the only reason is because we in our lab we only have one physical damper. So at this time we numerically model this damper as a numeric model in the second floor. So here is the videos of the real-time hybrid simulations. And this is these two-story buildings subject to MCE level earthquake. So you can see, so on the top right graph is the force displacement loop we measured in real time, emphasize its energy dissipation. And the bottom right graph is the moment curvature of the first story column. So you see this nonlinear behaviors. And also we comparing the story drift between the with the uncontrolled cases, which is there's no dampers installed. You can see we have a significant improvements by comparing the controlled and uncontrolled cases. And for next is kind of out of the topic, but I will still want to show you some applications under the wind load. So in here we are utilize these dampers in a 40-story steel structures. So this is 40-story buildings, and we assume it located in Los Angeles. It consists of a BRB frame in the middle and outrigger columns on its east and west side. And because it's a specific configurations, we're able to utilize the outrigger columns for damper installations. So we installed several, like almost about like 12 nonlinear viscous dampers in outrigger columns. But on the other directions, because we don't have outrigger columns, we're thinking to using this friction damper as 2-mass dampers to mitigate its wind vibrations. So here are some key features in here. To modeling these structures, the structure consists about like 1,318 nodes, and it's almost have nearly 3,000 elements, including these nonlinear explicit force-based fiber elements and nonlinear truss elements. And also you can see we only have one big viscous dampers in our lab, and then we numerically modeled the other 11 viscous dampers as numerical dampers, but using the nonlinear explicit Maxwell elements. But also we have this real-time model updating technologies where we update the dynamic parameters of these dampers in the real time for the viscous dampers. Now here is the videos of these structures under the wind loads. So the 3D wind loads we're capturing is from the aerodynamic tests we did in FIU facilities. And the top left graph is the top view of these structures. The wind is blowing in 45 degrees. You can see this structure have it's leaning on its 45-degree angles, and also have some vortex shedding effect. And then the second graph is the BRB hysteresis response. The structures behave linearly under wind load, but this element is the nonlinear elements. And the other two graph is the frictions energy dissipation loop and the viscous damper energy dissipation loop. And you can see these and these two different type of dampers have totally different dynamic behaviors. This is also the first 3D hybrid simulations results utilizing two different type of damping systems in our lab. So let's look at a quick on these actual controls, where I plot the synchronization plot between the target displacement and measured displacements. So you can see we also calculate the normalized room square errors for the actual controls for both dampers. You can see we're able to minimize reducing the errors by even smaller than 0.2%, which indicates very good actual control. And also we have the results about like 23% reduction of roof accelerations. But in here, so the dampers for the frictions is in its passive mode, where I ask the electric actors providing constant tension force. Right now, in our lab, we are studying a semi-active mode, so the results will be coming soon in this summer. So here's a brief summaries. So for my research in here, I introduced a new type of high-performance control system called banded rotary friction device, and then its application to two different type of buildings subject to earthquake and wind loads are showing to you. And the results show that this BRFD produced significant vibration reductions. But most important, the presentation I showed illustrates the real-time hybrid simulation capabilities of our facilities, and also by the method we use, we enabled real-time large-scale nonlinear simulations. So the key word is you always want to go for the nonlinears, and also the 3D effect is also very, very important. So I would like to acknowledge the EERI younger members communities to give me an opportunity to show my work. And also I would like to acknowledge the NHERI-EF network, and also our financial support is coming from the National Science Foundations. Thank you. So I'm going to pass and deliver the presentation to Casas.
Thank you very much, Dr. Cao. That was a very, very interesting presentation. Now we will continue with the next speaker before we move on to the Q&A, Professor Barbara Simpson. Dr. Simpson is an assistant professor at Stanford University. She completed her PhD at UC Berkeley and her bachelor degree from the University of Kansas. Her expertise is in developing innovative structural systems that improve building performance and reduce the effects of natural hazards. And to achieve this, she is using advanced computational and experimental methods. And with no further ado, the floor is yours.
Okay, well, thank you so much. I'm really happy to be going after the previous presentation, because now I get to go a little bit more into this idea of using real-time hybrid simulation to study this fluid structure interaction phenomena. And everybody can hear me okay, I'm assuming? No one's saying anything, so. Yes, okay, great, fantastic. So let's just get into the presentation here. So I'm going to briefly go over some motivation that sort of extends this idea of real-time hybrid simulation that was introduced previously to this idea of applying it to fluid structure interaction effects. And I'll sort of go into how we've been thinking about doing that. I'll also go into some applications and testing that we've been doing to look at cascading seismic and tsunami events, and then ongoing extensions that we're doing to study sort of multi-fluid problems, a little bit outside the typical scope of EERI, but I think a lot of our skills in earthquake engineering can start being applied to some of these other sorts of dynamical systems. So I think that'll be quite interesting. So let's start out with that motivation piece. So there's some challenges in simulating fluid structure interaction from either a purely computational or experimental approach. And we want to do these simulations because we know that our structures are vulnerable to these cascading effects of tsunamis and seismic loading. So this is an example from the Tohoku earthquake and tsunami sequence of Japan. Many of the bridges actually survived the earthquake, but then ended up failing under the subsequent loads induced by the tsunami. And I would just like to point out here that the way these loads interact with the structure, seismic versus tsunami, tend to be quite different. So that's something to consider. And so we want to do these simulations to better understand the behavior, response, and performance of our coastal infrastructure under sort of these cascading effects of tsunami and seismic loading. But really, we're constrained by sort of the financial cost of experiments, as well as some scaling challenges. I'll go into that in a second. And then the computational costs of simulating sort of wave and structure interaction in a computational software. And I'm showing this figure on the right here. That's the particle finite element method. It's actually sort of augmenting OpenSeas. And so that is a specific software where you can actually model the fluid and the structure at the same time. So you're actually able to model, say, previous seismic damage that's actually in the structure itself. But those types of software where you have both the fluid and the structural domains in the same software is actually quite limited. And so in addition to that, we're sort of also subject to this simulation paradox. which is, we need these experiments to sort of validate our numerical models. But when we start looking at the size and capacity of our existing wave facilities, where we're actually able to look at fluids impacting a structure, what we end up doing is if we're modeling at full scale, we're only looking at a specific component of the tsunami loading or specific component of the structure itself. If we look at an entire building, we get somewhat smaller. And then if we look at how the fluid loading might affect an entire city, we're smaller yet. And so there's this idea that we use these small scale experiments to validate our numerical models, but we actually don't really know if these experiments sort of model that small scale really reflect full scale structural response. So we have sort of this joint inconsistency where we don't really have the software to look at damage due to both earthquake and tsunami. And then in addition to that, we need to validate those numerical models with experiments, but these experiments aren't modeled at full scale. And so when I was previously at Oregon State University, we had discussed quite a bit whether we can use this idea of real-time hybrid simulation to sort of approach these challenges associated with modeling both a fluid and a structural domain. And so it's not a new method. It's been around for several decades, sort of developed in the late 1970s, early 1980s. And it was described previously, but just to give you a brief overview, traditionally hybrid simulation has really been applied to earthquake engineering, where you might model some of the structure in a numerical model. I'm calling it a numerical subassembly here, also sometimes referred to as a substructure. And then the part that you really know, but you don't know the behavior, you would model that physically in, say, a laboratory. So here I have one of the bridge piers on the right. And these two models, the numerical and physical model, are then coupled together through the equations of motion. In this case, in terms of structural dynamics. And so what you do is you integrate that equation of motion in time. That gives you a displacement at the next time step. You might also subject it to either a seismic loading in the physical laboratory, or in this case, it's in the numerical model. You get the displacement at the next time step, you virtually apply that displacement in the numerical model and physically apply it via some sort of actuation system in the physical model. And then you sort of look at the force response in the numerical and physical models, put those back into your equation of motion, and then move on to the next time step. And so combined, you sort of have this numerical model and this physical model that give you more realistic response, because in this case, the figure on the right, you might not really know how to model that numerically. And so we thought we could apply this concept of sort of partitioning the problem between a numerical and physical part. We could apply it to fluid structure interaction, except we have a more sort of severe partition in that the fluid, in this case, we model it physically, would then interact with some sort of numerical model representing the remaining structure. And the hybrid simulation is really the compatibility between these two systems. So it's going to make sure that we're sort of having as much as possible equilibrium and compatibility between the physical and numerical subassemblies. That's sort of what that equation of motion is doing. The great part about this partitioning is now we can sort of deal with this difference in scale. So we can take our physical model, which is modeling sort of the tsunami loading on, say, a bridge pier or a bridge deck. We can model that at small scale in our existing wave facilities. And then the remaining structure, we can model at full scale, and we can even subject it to previous seismic loading, because we have decades of experience dealing with seismic loading and the subsequent damage on our structures. Then we can use a hybrid simulation to sort of scale up or scale down any sort of information we're transferring between the two components or the two subassemblies. There's some other sort of advantages. So if we model the wave and the structure physically, then we kind of mitigate this computational cost associated with computational fluid dynamics or computational fluid structure interaction models, which tend to be quite slow. We also are modeling it physically, and there's a lot of uncertainties associated with that interaction of a wave impacting a structure. And so because it's physical, we can, provided we trust our boundary conditions in our laboratories, we can say that that's a real wave. On the right, on the structural side, now we can model our structure at full scale. And so we can sort of mitigate some of these similitude disadvantages that tend to come with the fact that we scale down our structure. It's really hard to simulate damage in a wave flume experiment or a wave Basin experiment. And we can also simulate significantly larger and more complex structures because now it's in a numerical model. And in addition to that, because it's a numerical model, we can swap out the numerical portion of our system quite easily to look at many different structural types. And so this is sort of this idea of this partitioning effect in hybrid simulation applied to fluid structure interaction. And so we did this in a pilot study to study the effects of cascading seismic and tsunami events. And what we did is we took a numerical model of a bridge, and we subject it offline to seismic loading. And so now the bridge is damaged, and then we took that numerical model and we coupled it to a physical experiment of a bridge pier at the Oregon State University large wave flume. And so, you know, very similar to what we had before in terms of the traditional hybrid simulation approach, except now we're sort of treating the wave loading. It's not quite like this, but I think for the sake of this conversation, it's sort of like applied loading on the right-hand side of your governing equations. And so now there's existing damage in the numerical model, and then we can see what happens when we subject that model to a subsequent tsunami. And so we've been calling this hydrodynamic real-time hybrid simulation, or hydro-RTHS. And we've studied it in a number of different cases, but I'm just going to kind of focus on this one here. So you have your numerical model of the bridge, and then on the right-hand side, we have the physical model of the bridge pier. And the really key part to this, and I'm really glad that there was this idea of rate dependency sort of talked about in the previous presentation, because as much as I would want my fluid to sort of behave like this and to be able to slow down, the reality is that because we have fluids in our physical model, it has to flow in real time. So there's a rate dependency that's sort of associated with the fluid impacting the physical portion of our system. So I mentioned we can sort of partition this against prototype and model scale, so full scale in our numerical model and small scale in our physical model to fit it into our flume. And so we can sort of, in this case, I'm using Froude scaling. We can sort of scale down the displacements or scale up the forces so that, you know, there's some compatibility between this full and small scale models. But in addition to sort of those scale factors, when you sort of scale between full scale to small scale, there's also scaling of time. You basically want your governing equations or the governing forces to sort of match between your full scale, in this case, numerical model, and your small scale physical experiment. And to get those forces to match, there's a time component. And so you also have to make sure that your numerical model is able to run fast enough to keep up with the small time scale associated with the physical loading in your experiment. And so there's sort of a need for speed, and that's where that real-time part of the real-time hybrid simulation comes into play. And so we did an experiment, and we actually looked at quite a few different ways of sort of pilot testing this idea of hybrid simulation applied to fluid structure interaction. So here I have the wave loading that's physical impacting a single bridge pier, and we take that loading and feed it back into our governing equations. And we can do things that are quite complex now that we would never be able to simulate in our wave flume or basin experiments in a normal wave experimental test. So because we have this numerical model, we're actually able to sort of copy that wave loading and induce it on both piers. And again, now we can actually look at the wave loading following some sort of seismic damage, because our numerical model is already damaged due to the previous seismic loading that we can apply sort of in an offline manner to our numerical model. And so this is sort of a rather poor video of that. But you can see this is our flume. You can see the pier at the end. This is obviously recorded with an iPhone. Keep in mind, this is a pilot study. And you can see that the sort of tsunami-like wave is going to come from our wave machine, impact the pier. That impact is, again, being fed into the numerical model. And the pier is then vibrating as a result of solving those governing equations. And so we've looked at sort of this idea of cascading seismic tsunami events sort of as a pilot study. And then we've been looking at a lot of extensions to this idea. So this is where I might be straying a little bit far from earthquake engineering. Because really when we talk about hybrid simulations, we're talking about partitioning a system. And so this type of simulation becomes really valuable when we're dealing with systems that have multiple dynamics. So one of the things that we've been looking at is floating offshore wind turbines, which are subjected to some aerodynamics. They're also, because they're floating, subjected to hydrodynamics. You have the structural dynamics, and then you have the servodynamics, or the controls that sort of control the top of the rotor, or the top of the turbine in this case. And unfortunately, each one of these parts of these systems is subject to different governing equations. And so when we go from full to small scale, we want to make sure that the forces that matter sort of are able to be similar between what's happening at full and small scale. But when you have multiple forces that are governing, say, to different parts of the system, then that becomes quite impossible as you look at small scale experiments. So for example, the wind tends to be governed by the Reynolds number, which is sort of this ratio of inertial to viscous forces. The structure tends to be sort of governed by this ratio of inertial to elastic forces. And then the waves, or open channel flow, tend to be governed by the Froude number, which is sort of this ratio between inertial and gravitational forces. And as you scale down your experiment, or as you scale down your turbine in this case to small scale, none of these things quite match up. And this was the same issue that we had with the cascading seismic tsunami events, except we were just looking at that structure wave part. Now we're adding one more component, which is that wave structure wind part as well. And so we've looked at sort of monopile wind turbines. So here we have the physical experiment. We've coupled that to a numerical model of the structure, as well as including some aerodynamics that we're loading at the top of the tower. And then we've also accounted for some soil structure interaction effects in our numerical model. So, if this is our physical model, it's just, a portion of the tower. Then our numerical model is the remaining structure, some wind, as well as SSI effects. And we're able to sort of mitigate these similitude inconsistencies by, again, having our numerical model be at full scale and then communicating with a small scale experimental model. It's just that these turbines happen to be quite large, and so as our turbine gets smaller and smaller scale, we again have to keep up with what's happening in real time in the physical model. And so our time scale, we actually have to compute computations very, very quickly. In this case, it was about a factor of 12, which means our time scale was shrunk to about a factor of 3. So we have to run 3 times faster than real time. And here's the experiment of that. You can see our cylinder and actuator at the top. And I know this is probably really hard to see. First, you see the wave loading is really quite different. So it's, more continuous type wave loading or periodic type waves. Actuator at the top, and I know it's difficult to see, but it is actually vibrating due to the wave loading that's being imparted on this structure. And here's just a difference where you can see the impacts of the hybrid simulation approach. So this black line is, just the experiment with just the waves. The blue line is just the waves coupled to a structural numerical model. So we have some of the hybrid simulation effects. And then this red one is numerical plus numerical wind plus a numerical partial structure plus the physical waves. So you can see that they're quite different. We're in the process of extending this to floating offshore wind turbines, which is something that we're going to see in the next decade on the West Coast. Our water is quite deep off the coast of the Pacific Northwest in California, which necessitates that if we're going to do offshore wind, it's going to be floating. And so we're in the process of looking at how we can take this idea of having a physical model of the wind turbine, have some numerical models of the wind, basically monitor what the structure is doing via sensors, feed that into a numerical model, and then sort of command some actuation system that represents that numerical wind. And again, we can sort of have some inconsistencies of scale and sort of mitigate the fact that everything's shrunk down when we test in our laboratories. So here's just a figure showing this, and then I just huge shout out to Akiri Seki, who's been working extremely hard on setting up this experimental test. So we're actually in the process of testing this week and next week at Oregon State for this project right now. So in summary, this idea of hydro-RTHS or hydro real-time hybrid simulation is a method that can allow us to better simulate the two domains of a fluid and a structure. So for example, wave research laboratories like those at OSU can now be virtually extended to look at more complex structural systems, including, say, damage due to a seismic events followed by tsunami loading. And we've just shown that it's feasible. There's still many, many challenges that we're working on, and we're still testing this on a range of applications. So just in summary, like how we typically think about wave structure interaction is you have a wave impacting a structure that tends to be pretty rigid, doesn't necessarily have damage from previous seismic loading. We could have some structural properties, say via spring added to the structural model, or we could represent some structural properties via an actuator. And the hybrid simulation approach is just going to allow us to really do something much more complex by having that numerical model represent a complete structural system. And so you can see that with this hydro-RTHS, we're really able to enhance the sophistication of our models and thus our simulations, and then our understanding of these cascading multi-hazard phenomena. And I just want to acknowledge the funding sources for the many projects that I've shown here, the great collaborators I've had, as well as the many students and postdocs that have sort of been collaborating on many aspects, different aspects of this project. And just some informal collaborations, mainly through a lot of discussions with how best to implement this, and thinking about sort of what would be the best way of simulating fluid plus structure. And thank you for your time.
Thank you very much, Professor Simpson. That was amazing. I really enjoyed the video.
Great, great.
So let's go to some Q&As. So first of all, an anonymous attendee asked, what is simulator exactly? Is it a MATLAB Python program using information from analytical and experimental data? This was when Liang was presenting, but I assume both of you can answer this. So,
Okay, so Barbara, you want to go first?
You go first, because I know we do it differently.
Yeah. So, I know you do GPU. So in the what we did is we using MATLAB and Simulink interface. So basically, we numerically model your structures using MATLAB, and then when we are doing the hybrid test, we convert it to a Simulink model. So, and then we also have the real-time HPC to providing the real-time signals. So Barbara, you.
Yeah, so we actually do something a little bit different. So Simulink is sort of a software provided by MATLAB that allows you to do sort of embedded systems, real-time simulation, hardware in the loop per se. And we've taken a slightly different approach. We tend to use a 3-loop architecture, which means that we take an experimental element that we then embed into an existing finite element analysis. That's like at least the typical approach that we do. And so then the method of communication between like how you actually embed that physical element, we tend to use sort of open fresco, which was developed at Berkeley. Andreas Schellenberg was a huge part of that. And then we use that to then communicate with, Simulink, then which communicates with the controller. And so it's like a slightly different flavor, but still uses that sort of Simulink interface.
Okay, great. Thank you both. Then Liang, this goes for you, I think.
Okay.
As far as I know, active system needs a lot of power. Why is it mentioned to require a low energy input?
Okay, I think this is part of my fault. So what in here, what I referring the one I proposed. So basically, I mentioned the high performance control systems, including active, semi-active, and hybrid damping systems. So this is a general frame. So of course, I totally agree. The active damping system require a lot of energy. So what we propose is semi-active damping systems. That's where I mentioned the low energy input to the large energy dissipations. I hope that answered that questions.
Okay, I think it does. Then I think this one goes to you, Liang, as well. You mentioned that structural system modification is uneconomical as a natural hazard mitigation solution. How does the cost of some the proposed high-performance control systems compare to the cost of a typical structural system modification?
Okay, so I think I also need to rephrase a little bit on this system modifications. So what I mentioned is uneconomical comparing with our damping systems is when I'm not saying like, okay, so it's all the case. So it depends on the modification level, right? So typically when we're dealing with multi-hazard, if you want the structures improve its performance under multi-hazards, so instead of using traditional systems modifications, we propose using our damping systems. And basically, to be honest, when we are fabricate this the damping, so the one we use, so that's why we always prefer using some existing technologies. The one I propose is the band brake. It's been there for been industrial for like decades. So all these fabrications is actually really like what we call cost effective. So actually, the most expensive part when we try to fabricate this damper is the material, the steel material we ordered. So and also because this potential for the multi-hazards mitigations. So this is what I'm trying to mention, is utilizing these damping systems is, I think, is much more cost effective for the multi-hazard mitigations performance.
Okay, great. Then Barbara, I have a question for you. Regarding rate dependency, the speed of the applied force on the physical model is affected by the speed of the actuator. Has this been an issue that the actuator is not fast enough? Also, for the tsunami loading, how could the wave speed be controlled?
I'll answer the first part because I don't know if I quite understand the second part, so I might ask you to ask that question again.
Okay.
But yeah, we haven't had an issue yet. So at least when I just showed like the linear actuator, I mean, that's a typical hydraulic actuator. We're really used to those in earthquake engineering. And we only went to a scale factor of like 1 to 12 in that case. And so we're really only looking at like speeding up real time by a factor of 3. What we're seeing with the robotic arm, which is how we're doing sort of the floating offshore wind turbine with the waves and with the wind as well. That's a scale factor of 1 to 50. So the time scale is quite different in that case. So it's square root of 50. And that we have lost some of the frequencies that we could potentially be interested in. And a part of that is not necessarily because that we can't do it. It's just because the robotic arm that we decided to purchase, which was cheap, might not have been the actuator of choice. So if you were to like go to Norway, for example, what they're doing is sort of like more of a cable motor type system, which, you know, they might be able to circumvent some of those effects that some of the challenges that we've had with the robotic arm. Some people have looked at maybe drones, where you have like a drone that's at the top of the turbine. You know, I'm not really clear on the advantages or disadvantages to all of those actuation systems, but at least in the robotic arm that we purchased, we could have probably bought a better robotic arm that's able to better keep up with the frequencies we're interested in. It's able to roughly get them, but like the structural frequencies tend to be quite higher than, say, the aerodynamic and hydrodynamic ones. So it just depends on what you're interested in. And then what was the second part to the question?
Yes, the second part says it has to do with the tsunami loading, and they ask, how could the wave speed be controlled?
Well, you could, if I'm understanding this correctly, you could flip the problem around, and you could have the wave loading being applied in a numerical model and that interacting with a full-scale structural model. If you're interested in sort of like the structural damage, in which case you can slow down the hybrid simulation. And so, you could have your numerical model, including the wave loading, sort of slow down real time. So long as your structure, it really just depends on what you model physically. So if your physical model has rate dependent effects, then it has to be real time or faster than real time if you're dealing with small scale. If your physical model doesn't really have any rate dependencies, say a typical structural system or structural damage, or that's what we assume anyway, then you can get away, then you can slow down what's happening in your numerical model. But, at least for us, we wanted to model the wave physically, because first of all, we had these amazing laboratory facilities at Oregon State, but also because it's incredibly complex. These models of the fluid are incredibly complicated. And they're very costly. They take a long time to run. And so we wanted to represent those effects physically. But of course, you could do the inverse of that.
Great, thank you. Then we have a question, I think, for both of you. For the hybrid simulation, how could we compensate for the lag of response between the experiment and the numerical analysis?
Well, you talked about that a little bit, right?
Yeah.
Yeah, maybe you take that one.
Yeah, I can answer this. So basically, the lag, first, of course, to do numerical simulation, you need to have a real-time machine, right? In Lehigh, we're using speedgoat. So everything's like your simulations go for real time. But most of the lag is actually coming from the experimental setup. This is what I mentioned before. I mean, no matter you're using the electrical actuators or hydraulic actuators, especially hydraulic actuators, they have a typically really high delay. So that's why you need to have a adaptive compensator to compensate this delay. But in general, so we are able to, we consider as a good value is as long as below to 10 milliseconds. So it should be a good it's good value for you to pursue the hybrid simulations. So in Lehigh, we're able to controlling the delays minimized is to below 5 milliseconds. But typically, when you're running hydraulic actuators, you will have 50 milliseconds to 60 milliseconds. It also depends on the capacity of your actuators.
And I will say, there's like another part of that too. I mean, that's just like the delay. You can kind of almost think about that as communication. So every time you add like another line of communication, there's going to be delays associated with that. And some of these systems, at least the ones I showed with the robotic arm, the communication becomes quite complicated. And every time you add something, there is a delay that you somehow have to compensate for. The other part of it is really the numerical model and how fast it's running. And, you know, I said in my presentation that this is going to allow us to look at more complex structural systems, but only to a point. I think the one, like the tall building response under wind loading that was shown with the dampers, I mean, that would be, I say, one of the more complex models that I've seen in hybrid simulation. And so there is like sort of a cap on how complex you're able to do on the numerical side before you sort of like it's too slow and it can't keep up with what's happening physically. So there's sort of two parts here.
Okay, then we'll have another question for both of you. Sardar asks if the hybrid simulations would be cost effective in practical applications.
We're trying. No, I mean that was the idea of the floating offshore wind. Like again, I mean, there's a lot of money being pushed at floating offshore wind or just offshore wind in general right now on both the east and west coasts of the US. And the idea was that this would be great for prototyping. So you could actually like maybe not only just model the wind in the numerical model, you could model some of the structural and servo dynamics, and maybe potentially like look at mooring lines, which tend to be sort of our wave basin fillies are rather shallow. So, and then that would be sort of a precursor to actually building like these very humongous systems out in the water for the actual prototype. So we've been envisioning this as sort of a prototyping type simulation method, in addition to advancing understanding. So I think we often get stuck in the advancing understanding, but this could easily also be used to prototype full-scale systems.
Liang, would you like to add something or we're good?
Yeah, I think I'm good. I feel like as long as you are kind of modern part of your models in the computers, comparing to with the full scale, you always be cost effective. It just depends on how you look at it, right? So if you compare with full scales, it's always cost effective. But if you're comparing to pure numerical simulations, you're always adding cost on it. So it's a trade-off.
Okay, so we're almost out of time. So I will ask one question to each one of you. So Barbara, for you first. Christopher asks, has the real-time hybrid approach been used to analyze the behavior of structural systems during aftershock events? Or are we capable of predicting this behavior entirely using numerical modeling?
If I'm understanding correctly, do you mean like a cascading earthquake tsunami event, whether we can sort of estimate those effects from a purely numerical standpoint? And I mean, we can, it's just that there's a lot of uncertainties there. Like our numerical models have to be validated by some sort of data, whether that's, you know, post-event reconnaissance data or whether that's experimental test data. Like at the end of the day, we need that validation. And right now there's a large concern that, you know, because of the challenges with our experimental test data and the fact that you can't, like, we don't necessarily have sensors during a real life data for reconnaissance, we might not have enough information to really validate our models, or we might be validating our models to data that might be inaccurate. And so at least for us, hybrid simulation is like a step towards not necessarily completely real life, because there's obviously some inconsistencies there, but more accurate than what we've been able to do in the past. I hope that answers the question.
Thank you. And now Liang Mohsen asks, what is the cause of torsion in the high-rise building during the wind loading? Okay,
so this wind load is a 3D wind load we measured on the wind tunnel. So, and the building is also 3D. So this is bidirectional wind load. So what we do is we build an aerodynamic model for these typical structures. So, and then we put it in the wind tunnel. And then we have a around 338 pressure type around the buildings to measure the real-time pressures. And then because you have all this pressure measured around the surface of building, you're able to calculate not only the bidirectional loadings, and also you can calculate this moment. And because this torus, right? So we are also, instead of only applying two-directional wind load directly, and we also apply this moment on the structures. So that's why you see these torted behaviors under the wind loads. That's why we also highlight why modeling 3D is way much more important, because only 3D models are able to capture this torted behavior. Yeah.
Okay, so for those of you whose questions were not answered, I think both Barbara and Liang would be happy to receive them through an email. And before I give the floor to Elizabeth, I would like to thank Barbara and Liang on behalf of the EERI YMC, and thank you for the very interesting presentations.
Hi, all right, let me get to the final slide here. Thank you all for attending. I just wanted to ask you if you have a moment to take time to complete the post-webinar survey that will pop up in your browser after this. You'll also get it by email tomorrow, so you can fill it out then. You can learn more about EERI at our website, and I want to acknowledge as well the funding that we received from FEMA, and the dues of EERI members like yourselves are what allow us to put on webinars like these. I linked in the chat, but there's a PDH form available, and the URL is visible here. And then also, if you look in the chat, I've just added a registration link for a webinar that we'll be holding on March 20th on Monday at 11 a.m. Pacific time, with the EERI Gear Advanced Reconnaissance Team to Turkey, surveying, talking about their findings in their initial survey of the impacts from the earthquakes there. So we hope you'll join us for that as well. Thank you, and thank you again to our speakers for such a great webinar.